We are going to use Euler's method again to obtain an approximation, but instead of doing a bunch of computations using a calculator, we're going to ease our work by using a spreadsheet. Our differential equation is y prime equals 2xy. Initial condition is y of 1 is equal to 1. The approximation we're trying to achieve is y of 1.5. We're first going to use a step size of 1/10 and then a step size of 5/100. Now the way I'm going to use Excel here is I'm first going to tell myself what the step size is. It's more than just telling myself, we're actually going to use that. Then what we're after is a bunch of ordered pairs, x sub n and y sub n. Our starting values are 1 and 1 according to the initial condition. And what we need is f of x sub n, y sub n. Now this is just a note to myself, equals 2xy. So now I know what formula I'm going to enter in here. We'll get back to that. First, I'm going to generate our x values. So here I'm going to say x sub 1, if you will, equals the previous x value plus our step size. And I'm going to use what's called absolute referencing. On a Mac, it's Command T. On a PC, I think it's Shift F4 or something. Look up absolute referencing. And what that'll do is it'll continuously reference that cell. So that here, when I drag this down, cells will populate. Now let's come over here and generate some function values. According to our rule, f of x sub n is equal to 2 times x sub n times y sub n. And then, according to Euler's formula, our new y value is equal to the previous y value plus the step size, I'm again going to use absolute referencing, times the f of x sub n, y sub n. Now I'm going to take this formula that's giving our f value and drag it down. Then I'm going to grab the y and the f values and drag them all the way down here. We have filled in a bunch of f values, but we've also filled in a bunch of y values. And this point right here, 1.5 comma 2.9278, is giving me the approximation that we're actually after. I've imported the spreadsheet result here, and we can say then that y of 1.5 is approximately, to 4 decimal places, 2.9278. Now we're asked to construct a table that has estimated value. That's what we have here. Actual value. Now actual value is found by solving the differential equation. Y prime equals 2xy is a linear equation. It's also separable, but I'll go with linear. Y prime minus 2xy is equal to 0. And we can see here that mu is going to be e to the negative x squared. Then the derivative with respect to x of e to the negative x squared times y is equal to 0. E to the negative x squared y is equal to c. So y is equal to c e to the x squared. And the initial condition of y of 1 equals 1 is going to give us that c is equal to e to the negative 1. So y is equal to e to the x squared minus 1. Back to our spreadsheet, I'm going to copy and paste our x and y values. But when I paste them, I'm going to paste special and go to values instead of formulas, because all of these x values depended on the computations that we had up here. This way, they're just numbers in the cells. And then we're going to find actual values based on our solving the differential equation. So here this is going to be equal to the exponential function. Excel knows that function. And it knows it as a function, so I need to use function notation. And remember, it was e to the x squared minus 1. And of course, our actual value for x equals 1 is y equals 1. That needs to be the case here. But now when we drag this down, we can see that the actual values are starting to depart from the approximations that we had. Well, by how much? That's where error comes in. We're going to look at the absolute error and the relative error. Absolute error is going to be the absolute value of the actual value minus the approximation value. And because it's absolute value, the order of subtraction doesn't matter. And then I'll just go ahead and drag that down. And we see that the absolute error turns out to be, for x equals 1.5, it's about 0.56. Now, is that a big error or a small error? And that's where relative error comes into play. That's going to be equal to the absolute error divided by the actual value. So you have to know the actual value in order to compute the relative error. And then I'll hit enter, and we're going to format this as a %. For that, I'll come up here to the menu and just tell it it's a %. Then we'll get rid of that. Dragging that down and then giving it a couple of decimal places for context gives us that the error associated with x of 1.5, so our approximation of y is approximately 2.9278, has a relative error of about 16%. We're going to repeat that using a different step size. For that, I'm just going to add a new sheet here. We want to change the step size to 0.05. And notice that takes our x values only down to 1.25. So I'm going to throw in some additional rows, and then I can actually just drag the formulas down to give me a new y value associated with x is equal to 1.5. You'll see I also inserted some rows into the comparison table below. So to flesh some of that out, I'm going to copy and again just paste the values. And then recopy these formulas down here. And we can see that the new relative error associated with x equals 1.5 and for the y value of 3.1733 is about 9%. I've added screenshots of that Excel work into our working document here, where we can see that for a step size of 0.01, y of 1.5 is approximately 0.9278. For a step size of 0.05, we have y of 1.5 is approximately 3.1733. The numbers, yeah, we're supposed to produce numbers, but it's not so much the numbers here that I'm interested in as the process, right? This recursive Euler's formula. Also, I'd like to point out here what happened with the error. When the step size was cut in half, we found that the error was also cut by about a half. Now, you're going to look at 16 and 9 and say, that's not half. And no, it's not half. But it's about half. And I'm going to let that sit for now, but we're going to come back after a later lesson and compare what happens to the error when the step size is changed.